In Chapter 10, we'll look at dot structure, shape, and polarity of molecules. Dot structures for the elements give the element a dot for each valence electron. So to review, remember the valence electrons are the column that it's in. So this first column has one valence electron. The second column has two valence electrons. The third has three, and so forth. So each column, the column number, tells you how many valence electrons. And so you can see that in these pictures, that each element has that many dots around it. And the elements in the last column, column 8, are particularly stable because they have the octet. They have the complete set of 8. You can see how these Lewis structures show ionic compounds. So take, for instance, sodium chloride. Sodium has one valence electron. Chlorine has 7. If sodium were to give its valence electron to chlorine, then it becomes the chloride ion with 8 valence electrons, and that's complete. That's the magic number. Now, sodium looks like it has no valence electrons, but the shell below it is now complete. And so each of them now have a full shell as they form the ions. Same idea with magnesium. It's going to give 2 electrons to oxygen. So the magnesium becomes +2, the oxygen -2. For calcium chloride, calcium has 2 electrons. So it's going to give 1 to one chlorine, another to another chlorine. And that's why it comes together as CaCl2. So we've looked at other ways to make the ionic compounds, but the dot structures also show that. When we get to covalent molecules, now nobody wants to give up their electrons. So instead, the electrons are shared. So this example with water here, you can see oxygen has 6 valence electrons, hydrogen has 1. Now, hydrogen doesn't necessarily want to give it up, but if hydrogen comes and just sits right here, and another one right there, you can see how now oxygen has a full 8 electrons, and hydrogen now has 2. 2 is a full shell for hydrogen because it's in that first row, and that only has 2 electrons in the first energy level. And so those 2 shared electrons, instead of drawing it as 2 dots, we usually draw it as a line, and that line represents a bonding electron. It's a pair of electrons, 2 electrons, that bond the 2 atoms together. So we can always just bring the elements with their electrons to draw the Lewis dot diagrams, but sometimes as the molecules get bigger, a systematic method becomes more helpful. So here are the steps written out for drawing dot diagrams, and I'll go through them as I do some examples. So let's start with F2. The first step is to count the total number of valence electrons in all the atoms. So F has 7 valence electrons, and we have 2 of them, so 7 times 2 is 14. And that's our total number of valence electrons. Now, if there were a charge, we'd have to include that as well. The next step is to arrange them in an order. Now, this one's very simple because it's 2 atoms, so we'll just put them next to each other. So put F next to F. So those are our 2 atoms. And then we're going to connect them with a line. And what that line represents is 2 bonding electrons. And so now what I'm going to do is subtract from my total of 14. And now we have 12 electrons left to put in our molecule. So that's step 4, subtracting the bonding electrons from the total. And now we'll arrange the remaining electrons around the atom, starting from the outside and giving each element an octet, okay? So right now each fluorine has 2 electrons, but what it wants is 8. 8 is the number that they all want to get. So I'm going to draw 6 dots around this fluorine, and then 6 dots around this fluorine. And now each fluorine has 8 valence electrons. 6 dots plus the line that they both get to count is 2, so that gives them 8. I've also used up my total of 12 remaining electrons. So 14 total electrons 2 are the bond, and 12 are the dots. And so step 6 doesn't apply here, or does step 7. So that is our Lewis structure for F2. And you can see why fluorine is diatomic. It's so much more stable like that, and all of the halogens are diatomic for the same reason, because they all have those 7 valence electrons. All right, let's look at methane, CH4. So carbon has 4 valence electrons. Notice I'm getting that number from right here, 4. It's in column number 4. And hydrogen has 1 valence electron times 4 of them. So I have a total of 8 valence electrons in this molecule. So that is my first step. Step 2 is to arrange the atoms in a structure. And in this case, we have more than 2 atoms. And so what we want to do is put carbon in the middle. Anytime you have carbon, it's going to go in the middle. If you don't have carbon, whatever element is closest to the middle of the periodic table is usually in the middle. So I'm going to put carbon in the middle and put hydrogens around it. So that is the arrangement for my molecule. And now I'm going to connect all of these with a single bond. So draw a line between all of these, connect with a single bond. And now I'm going to subtract how many electrons I've used in my bonds. So each line represents 2 electrons. So I have 2, 4, 6, 8 minus 8. I have no remaining electrons. But that's okay for this molecule, because hydrogen wants 2 electrons, and it has it. So once you give hydrogen 1 bond, you're done. That's 2 electrons. That's all it can handle, and that's the stable configuration. So the hydrogens are all good, and the carbon with 4 bonds, 4 times 2 electrons each, carbon also has 8 electrons, and that's a good number for carbon. Let's do a few more of these, and if you'd like to, pause the video right here and try these on your own, and then you can turn it back on and check your answers. So NF3, starting with the valence electrons, nitrogen has 5. Fluorine has 7 times 3 is 21. So that gives us a total of 26 valence electrons. For the structure, we're going to put nitrogen in the middle and put fluorines on 3 of the sides. And it doesn't really matter which side you pick. Just 3 of the sides are going to get fluorines. We'll connect them all with a single bond. So here's our bonds. And so that is 3 bonds. So I'm going to subtract 6 bonding electrons, and I have 20 left. So 20 is the number of dots I'm going to make. Starting on the fluorines, so each fluorine wants 8. It has 2 because it has a bond, so I'm going to put 6 dots on each fluorine. Okay, and so 6 times 3, that is 18 dots. I still have 2 more because I need to do 20 dots. And the last 2 are going to go on the nitrogen because it only has 6 and it wants 8. So there's my structure. C2H6. Carbon has 4 times 2 is 8. Hydrogen, 1 times 6 is 6, for a total of 14 valence electrons. Now this one, since I have 2 carbons, I'm going to put them both in the middle. So put carbon bonded to carbon as the middle, and I'm going to arrange the hydrogens evenly around them. So I'm going to put 3 hydrogens on this carbon and 3 hydrogens on this carbon. And let me erase that little mark that happened there. My pen's kind of hard to write with, so erase that and go back to the pen. All right, so this is our structure, and all those things around the carbons are hydrogens. They don't look that great, but there we go, hydrogens. And if we count up the electrons that we've used in the bonds, we have 1, 2, 3, 4, 5, 6, 7 bonds. So 7 bonds times 2 electrons each, we have 14 electrons in the bonds. So we have no electrons left. So we can't make any dots in this one. And we check if everybody has 8. Now remember, the hydrogen's 1 bond and you're done. So the hydrogens are all good. And each of the carbons has 4 bonds, which makes 8 electrons. So those are also good. So that is our dot structure. Let's go to O2. Oxygen has 6 valence electrons times 2 gives us 12. So we have 2 atoms, so we'll put oxygen next to oxygen and connect them with a bond. So there's our bond. Subtract 2 for the bond, and we have 10 electrons left to make dots. So remember, each oxygen wants 8. Right now it has 2. So I'm going to put 6 dots around this one. And then I'd like to put 6 dots around this oxygen. But right there, I ran out of dots. 10 is my number. I can only make 10 dots. And so now we find ourselves in a position that we've used up all our electrons, but the atoms don't all have 8 yet. And when that happens, we need to share more. So imagine if we took these 2 electrons, and instead of just letting this one oxygen have them, we put them in the middle. Now both of the oxygens can see that electron. And so now let's erase them from here. And so now each oxygen has 8. And we have a little dot that shouldn't be there. Let's get rid of that dot. So 2 bonds makes 4 electrons. So each of the oxygens has 4 electrons in the bond, and then it has 4 dots, so each oxygen has 8. So that is an example of a double bond. You make a double bond when you don't have enough electrons to give everybody 8. All right, looking at carbon dioxide. Carbon has 4, oxygen 6 times 2, that's 12. We add those together and we have 16 electrons. So we'll put carbon in the middle with an oxygen and an oxygen. And so now we have used up 4. So subtract 4 and we have 12 dots. So I'm going to put them on the oxygen first. So I'll put 1, 2, 3, 4, 5, 6, and then 6 on this oxygen. And now the oxygens are good. They both have 8 electrons, but the carbon doesn't. The carbon only has 4 electrons. And so, again, we're going to need to make a double bond. So we're going to take these electrons, put them in the middle, take these electrons, put them in the middle. So we'll erase that, and so this time we made 2 double bonds. Now, what about this structure? This structure also has 2, 4, 6, 8, 10, 12, 14, 16 total electrons, and everybody has 8, but it's not as good. And the reason it's not as good is because oxygen with 6 electrons really would prefer to make 2 bonds. So if you think about oxygen, 1, 2, 3, 4, 5, 6, it'd like to make a bond right here and a bond right there. So if oxygen can have 2 bonds, that's its favorite. It doesn't always have 2, but that's a better structure. And so we're going to take the 2 double bonds over a triple and a single. It's a better structure. Let's look at C2H4. Carbon has 4 times 2 is 8. Hydrogen has 1 times 4 is 4 for a total of 12. So we have 2 carbons. We'll put them both in the middle. And 4 hydrogens, so we'll put 2 hydrogens here and 2 hydrogens here. Okay, subtracting our bonds, we have 1, 2, 3, 4, 5 bonds. So that's 10 electrons, which leaves us 2 dots. Now we go to figure out where do we want these 2 dots. The hydrogens don't need them. But when we look at the carbons, they actually both need the 2 dots. And so instead of putting the dots on this carbon and leaving that one short, or putting them on this carbon and leaving the other one short, we're going to put them in the middle. And so that's going to be a double bond because we didn't have enough. Both carbons wanted the electrons, so we put them in the middle. Let's look at nitrogen. Nitrogen has 5 valence electrons times 2 gives us 10. So we put nitrogen next to nitrogen, and we've used 2, so subtract 2. That gives us 8. Now if we put 6 on this one, which is how many it needs, that only leaves us 2 for that nitrogen. So we don't have enough electrons to give both of them 8. So let's go ahead and take these and put them in the middle. Now our first nitrogen looks okay because it has 8, but our second nitrogen is still lacking. It only has 6. So we're going to have to do that again and take these, put them in the middle. And now both of our nitrogens have 8. So let's erase these, and this is a triple bond. So this is an example where we had to share electrons even more than the double bond. So the rule is if you're making a double bond, you only do that if you don't have enough electrons. And again, you move on to the triple bond only if you don't have enough electrons with the double bond. Another thing we see here is why the diatomics are diatomic. So we've really looked at all of them. We looked at all the halides and why they are diatomic. And we looked at oxygen and nitrogen. And hydrogen is similar to the halides as the 2 hydrogens share. So this explains why the diatomic elements are diatomic. Looking at the carbonate ion, we have something new. We have something with a charge. So let's look at how we address that. We start out by adding up the valence electrons. So carbon has 4, oxygen has 6, times 3 is 18. So that gives us 22. But since we have a -2 charge, what that means, a negative charge means more electrons. So we're going to add to this 2 more electrons to give us 24 total electrons. So that's how you deal with a charge. If it's negative, you add the electrons. If it's positive, you subtract. So now we'll make our structure. We'll put carbon in the middle, and we'll put oxygen, oxygen, and oxygen. And so that used up 6 electrons for 3 bonds. So we have 18 dots to make. So I'll go around the oxygens, put 6 dots on each oxygen. And that uses up the 18 electrons. And now all of our oxygens are complete with 8, but the carbon only has 6. So what we have to do is make a double bond. So I'm going to take these 2 electrons and move them to the middle. And we'll erase them. And you may be tempted to do that to all of the oxygens, but that would give carbon too many. So we only do it to one of the oxygens because now carbon has 4 bonds, and so that gives it 8 electrons, which is complete. The other thing we need to do is put brackets around it and give it a -2 charge. So anytime you have an ion, you put the brackets and give it a charge. You may be wondering, why did I put the double bond on that oxygen? Wouldn't it be just as good to put the double bond on one of the other oxygens? And looking at this structure, it's just as good as the first structure I wrote. They're both equally valid. And so when you have more than one valid structure, you draw them both and put an arrow between them, indicating resonance. And for this particular molecule, we have one more, because we could have put the double bond on this last oxygen as well. So we have 3 equally valid structures, and that's resonance. So that's how we deal with this with Lewis structures. We draw all 3 of them with arrows between them. And the real structure is really not any of these. It's a blending. So all the oxygen-carbon bonds are the same, and they're about 1 1/3 bonds. So that's what resonance is. Let's look at sulfur dioxide. Sulfur is right here. So it has 6 valence electrons. So we have sulfur with 6. Oxygen also has 6. Times 2 is 12. So we add those together and we have 18. We'll put sulfur in the middle with oxygen and oxygen. And so that used up 4, so we'll subtract 4. So now we have 14 electrons. Start with the oxygens, give each oxygen 6. That's 12 electrons. We have 2 more, and sulfur needs some more electrons, so we'll put the 2 more on sulfur. And you really might have wanted to put 2 more on sulfur, but we're out. That's 14 dots, and so we have to stop. But sulfur doesn't have enough. The oxygens are good. So again, we're going to need to make 1 double bond. So I'm going to take these dots and move them to the middle. And it really doesn't matter which pair of dots we move to share, but that's how we make a double bond. And again, we only need 1 double bond because now sulfur has 8 valence electrons. We don't want to give it 10. 8 is the right number. And you might recognize that this one also has resonance. So I could have drawn it with the double bond on the other oxygen. And so these are the 2 resonance structures for SO2. So both of those molecules has resonance. Here's all of these worked out maybe a little bit more neatly if you couldn't read any of that writing on the previous slides. This one also shows shape and polarity that we're going to get to a little later. Double and triple bonds are shorter and stronger than single bonds. One example, the diatomic nitrogen is a very strong short bond, and the bond is so strong that it's difficult to break, making nitrogen relatively unreactive, which is helpful because most of what air is nitrogen. Resonance we've already talked about, and we've talked about this particular molecule, but I put this in because the picture is a little bit more clean, and it shows how both structures are valid. They're equally valid, and so the real structure is a blending of the 2.